So I will talk about the sum squares, the polynomial optimization. So basically, we will study how do we like use the sum squares technique to approximate some polynomial optimization problems, and we will see how this how can we solve the sum square program using the semi-definite programming. So so I will be, so this material is from the book. Let's share my screen. So share my screen. So you seeing this? It's my screen.
Yeah.
So this is the book by Pablo and Parillo and Gregory and Beckhurst and Thomas, by these people, called semi-definite optimization and convex algebraic geometry. So you can see this these chapters. Yeah. So they are so the first two chapters is very basic stuff. Chapter 1, chapter 2, and today I will mainly focus on chapter 3. So I will be roughly following this this chapter. Yeah, and so I'm not going to talk about the other chapters, maybe a little bit. Okay, so you know that in the book, this book is. So let's go back to the to my screen. So so we consider the polynomials in n variables with real coefficient. So we say a multivariate polynomial px1 that xn is non-negative if it takes only non-negative values. So i.e. the following, we have a p x1 xn x2 xn is non-negative for all x1 xn in the real. So there are three types of questions. The first question is the decision question. So given a polynomial px, how do we decide if this polynomial is non-negative? And the second is the certification problem. So we ask, it is possible to certify non-negativity efficiently. So it means if a polynomial is non-negative, you want to certify it to convince someone else that this polynomial is indeed non-negative. And the third question is the computational complexity to decide polynomial non-negativity. So these are the three types of questions we want to study. First, let's see some basic definitions. So the definition that and Pn 2D be the set of actually let me share my screen. I think I can share my screen within my computer. 1 second. I think this is better. Okay.
Yeah, looks good.
Yeah. Now I can use this. I can share the screen and then use the Zoom whiteboard to draw something if I want. So yeah. So the basic definition first. Let Pn2D be the set of non-negative polynomials in n variables of degree less or equal to 2D. So when I say degree, I mean all the summations of the degrees for each variable, right? So if I have a variable, I have a monomial x2, y1, then this degree is 2 plus 1 is 3. Or if I have monomial x2, y2, then the degree is 2 by 2 plus 2 is 4. So this is this Pn2D is the set of non-negative polynomials in n variables of degree less or equal to 2D. So there's a theorem that this Pn2D, this set of non-negative polynomial, is a proper convex cone, which is easy to say. So proper, it means it's close, pointed, and solid. Okay. So let's say an example. How can we show that a polynomial is non-negative? So we consider this quadratic polynomial. Px equals 1/2 times x transpose ax plus 2 transpose x plus c. Well, it can be shown that this polynomial Px is positive, is non-negative, if and only if this matrix A, B, B transpose C is positive semi-definite. So positive semi-definite means all these polynomials are, all the eigenvalues are negative. Or equivalently, you can say if or equivalent if a matrix, a symmetric matrix, is positive semi-definite if for all x transpose times A times x is a non-negative. So so the proof is how do we prove this? Prove this claim? So A, B transpose C is non-negative. It implies x transpose 1, A, B, B transpose C times x1 is non-negative. So for all the x in Rn, and then we expand this this quadratic term. So this is exactly Px being non-negative. So this is the one direction.
By this you mean positive semi-definite, right?
Yeah.
Okay.
Yeah, this matrix is greater means it's a positive semi-definite.
Okay.
But x transpose 1, this is a scalar, so this is being non-negative. Yeah. Okay, and then for the other direction, so if I have a so let's see, yeah. So so if I have a Px positive for Px non-negative, then I have x1 this one is positive for all x in Rn. And that means that means actually this one. So x transpose 0 times this matrix times x transpose 0 is the negative. Why? Why we have there here we have 1, here we have 0. This is 1, but this is 0. And that's because if this thing is it's strictly negative, then I can perturb this 0, right? I can perturb 0 by arbitrary small epsilon, and then this will still be strictly negative, and therefore I can scale this epsilon, right? I can scale it so it multiply some very large number, so it becomes 1. So eventually I will have something. I have something like 1 and x transpose here, and x1 transpose 1 times a b transpose c times x transpose 1 is being strictly negative. So this contradicts this condition. So therefore, x transpose 0 times this matrix, this big matrix, times x0 is a positive, is a negative for all x in Rn. Therefore, by the definition of the positive semi-definite matrix, I claim that AB B transpose C is a positive semi-definite matrix. So I prove this claim that for quadratic polynomials in n variables, it's not negative. It's being non-negative. It's equivalent exactly as equivalent to a SDP optimization problem. Okay, so however, this is very nice. So it's not case for other polynomials. For other polynomials, we may not have this nice property that non-negativity is equivalent to positive semi-definite. So therefore, we will introduce some squares. So the definition of some squares is such that px is equal to k equals is some squares, right? So it's equal to the qkx, and k is from 1 to m. So each qk square is so qk square x is a square, and then px is a some square. So there's a notation of the some square polynomials in sigma sum n2d denotes the set of some square polynomials in n variables of degree less than or equal to 2d. So we have this Hilbert's. So we know from Hilbert theory that the negative polynomial is the set of the negative polynomial is equal to the set of some squared polynomial. Only in the following 3 cases. First, in the for univariate polynomials. Second, for quadratic polynomials. And third, for bivariate quadratics. So bivariate quadratics, I mean there are n equals, there are two variables, and the degree is 4. The maximum degree is 4. Okay. So for all the other cases, there always exist non-negative polynomials that are not sum of squares. So here is the example by Moskine. So Moskine polynomial, which is x4 y2 plus x2 y4 plus 1 minus 3 x squared y squared. So we can verify this polynomial, the non-negativity of the polynomial using the geometric arithmetic mean, right? So I have so 3a plus b plus c divided by n is greater or equal to the third is greater or equal to a times b times c to the power of 1/3. Yeah, this is 3. So generally, this you can replace this 3 by n. So that shows that and then multiply this by 3, both sides by 3, and then by putting the right hand side to the left hand side, then we get that that the Moskine polynomial is non-negative. But this polynomial, Moskine polynomial, is not sum squares, unfortunately. So how do we prove it? So we use the so-called Newton polytope to prove this claim. So what is the Newton polytope? The Newton polytope is the Newton polytope of a polynomial is the convex hull of the points assigned to each monomial. So let's say this example. Let's see. So for our Moskine polynomial, right? So so you see this degree, the biggest, the first term is x4 y2, and second term is x2 y4. Therefore, so we have a point here. We have a point here, x2 y4, and then we have a point here, x4 y2, and then of course we have 0 0. So then you draw the convex hull. So you just connect all these nodes, all these points, and then all the monomials of our of the Moskine polynomial is inside this the convex hull, the blue triangle, right? So now we can see that let f be a sum squares. If f is a sum square, so f is equal to the sum of gj. So gj is a square, and then what is the Newton polytope of monomial g of the monomial in the what's the Newton polytope of the squares? I is g, is g, right? So it's then it turns out that this Newton polytope f is 2. The Newton polytope of f is 2x, where x is the Newton polytope of the squares. G with GG. G. So in this picture, the blue triangle is the Newton polytope of the Motzkin polynomial, and if Motzkin polynomial is some squares, then this blue triangle, sorry, the red triangle is the Newton polytope of the squares of the squares, and you can see this the red triangle is exactly 1/2 of the blue triangle. So therefore, if Motzkin polynomial is some squares, then we can write this as it as this form. So mxy is equal to the sum of ax squared y plus b x squared plus cxy plus d, and this x squared y, xy squared, xy and d are all in this red triangle. And this is impossible since in the Motzkin polynomial x, let's go to the Motzkin polynomial here. We have the coefficient of x squared, y squared is -3. But here, the only we get the coefficient of x squared, y squared must be some c square, right? The sum of c squares. So this c square must be positive or negative. So that's a contradiction. Okay, that's the proof that why the Motzkin polynomial is not a some square. So okay. So far, are there any questions?
It's good.
Okay, good. No question. Then I will proceed. So now I will talk about how using semi-definite programming to certify some squares, right? So we instead of just using handwritten proof. So let's first see this example. We consider this univariate polynomial, and suppose this and we can write this px in this matrix form, right? Matrix product form. Yeah, and this matrix is a symmetric matrix. So px is 1x x squared plus times this symmetric matrix in the middle and 1x x squared. So if because for univariate polynomial, some non-negativity is equivalent to some squares. Therefore, if this let's call this this matrix as Q, this big matrix as Q. Right? Therefore, if this px is negative, then there must exist a Q, which is positive semi-definite. So now we match the coefficient, right? We expand this product, these products, and matching the coefficient. So Q22 is x4, right? So this is yeah. So Q22 is correspond to x4. So which means Q22 is 1. And for x3, so we have so 2Q12. Yeah, 2Q12. It's 4. And for x squared, so x squared is x times x, So which would be Q11 plus x2 times 1. So there are two of them. So Q11 plus 2 Q02 is equal to 6. Right, so that's the coefficient corresponding to the x2 term, and for x term, x is 2 Q10 is equal to 4. Yeah, and Q00 is equal to 5. So now we have a SDP feasibility problem. So we want to find a Q, which is positive semi-definite, such that these conditions, this condition 1, all these conditions, all the linear constraints holds. We can throw it into a SDP solver, like in MATLAB, and then we get this solution. So Q can be, we found this Q. Q is this matrix, and it's positive semi-definite, so it can be written as a V transpose times V. The V is this matrix. So Q can be written, therefore Px can be written as a 3 sum squares, a sum of 3 squares. So first term is x squared plus 2, right? So which means here this 2 it corresponds to x, and 1 is the coefficient of x squared. So the first term is the first square is the comes from the first row, so 2, which is x squared plus 2x plus 0, and second square comes from the second row, which will be square root of x plus square root, and then you make, and then the squared, so there is a 2, and similarly for the third term. So this is the example for the univariate case, for univariate polynomial. Now we let's see a multivariate example. Okay? So let's say we have a bivariate polynomial pxy. This can be done similarly. So we want to verify we want to see if this polynomial can be written as some squares. Then again, we first write it as a matrix product form, and then equating the coefficient. We equate the coefficient of the monomials, and there are n plus d choose d, which are 15 affine constraints. So that's another. And then there's this equivalent to another SDP problem. So now we see how can we replace the non-negativity constraint as the sum squares. So let's see the application, right? So how do we apply this sum square technique to polynomial optimization? So first, let's see the following question. So we minimize Px. This is so Px is polynomial, which a univariate polynomial, and and there's this an unconstrained optimization problem. So no other constraints. So a simple observation is that a number gamma is a global lower bound of Px if and only if Px minus gamma is non-negative. Right. So this is gamma is the lower bound of this optimal minimizer if and only if Px minus gamma is non-negative. So now we can convert this our minimization problem into a maximization problem. So instead we maximize gamma subject to px minus gamma being negative, and for all these for all x in R. So this problem is a convex problem. This is the feasible set. The feasible set is defined by an infinite number of affine constraints because they are infinite values of many values, infinitely many values of x, right? So for each value of x in the real, and then we plug in x in, and we get affine constraint for gamma, and there are infinite many of them. So this is the convex problem. So that means we can convert this into a some square program. So as we see previously, a univariate polynomial is the negative is equivalent to saying so px minus r is the negative is equivalent to saying px minus gamma is some squares. So this is a SDP problem, and which can be solved by SDP solver. Okay, so let's say an example how. So for example, px is x4 minus 20x squared plus x, and then we want to minimize px. So instead we maximize gamma such that x4 x minus 20 x squared plus x minus gamma is negative for all x belongs to R, and this and then this is equivalent to some square problem, which is equivalent to a SDP. So we max gamma such that this q this 1x squared default, this is this one holds, and so q is the following. Q is so the top left is minus gamma, right? Because we have a minus gamma here. So that's the top left is minus gamma, and then we have other constraints by equating the coefficient of the monomials. So Q3 equals 1. That means Q3 is the coefficient of x4. So Q33 is 1, and then there are some other constraints. So in the end, we get this. We will obtain this STP problem. So we maximize minus Q00, which is the top left element of Q, such that Q is part of semi-definite with this affine constraint. Okay. So this is a univariate example. Now let's look at the multivariate case. So multivariate optimization. So similar to the univariate, we have this. We can convert when we minimize a multivariate polynomial. We could maximize gamma such that p x1 the xn minus gamma is the negative. And then there's a we approximately approximate this problem by a sum square problem. So so this so instead we say px1 dot xn minus gamma is a sum square. So which it's obvious that obviously the p sum square psos is less or equal to p star, right? Because psos is this sum square program. Since sum square implies non-negativity, but non-negativity is may not imply sum square for multivariate cases. So this sum square, this one has a smaller feasible set than this problem. So since it has a smaller feasible set, the maximum value must be no greater than the first one. So we have this equality, but fortunately for many relatively small problem, we often have a p sum squares equal to p star. In situation where PSOS sum square is strictly less than p star, what we can actually produce stronger SOS sum square condition that will converge to p star. We will talk about this later. So we will see how we can solve a series of sum square problem, and such that this it converges. It eventually converges to the optimal value of the previous of our previous of our polynomial optimization problem. Right. Yeah. So. Yeah. So now let's talk about this sum square of rational functions. So let qx be a sum squares. Qx equals sum of qix square. Then we have a qx times px equal to the sum of sjx square. So if qx times px is some squares, yeah. So yeah. Then qx times px is the summation of sjx, and therefore we can write px as px equal to we divide qx from both sides. So eventually px equal to after some calculation. So we put qx here, and then so 1 over qx becomes qx divided by qs square. And then since qx is some squares, so we replace this qx by some qix squares. Eventually that we have a qx times px is some squares. So it's some rational squares. So yeah. So if qx and px is some square, then px is some rational squares. So so what this used for? It tells us that if px is not a sum square, we can multiply px by qx, where qx is a sum square, and then we can, and if qx, if after multiplying px by multiply qx, if this product qx times px is a sum square, then we can actually write px as a sum of a rational sum squared of rational functions, right? So on in the other way, if we can write px as a sum of a square of rational function, then we can multiply the the biggest multiply the denominators of, and we can multiply the denominators of the rational functions, and then so this qx, i.e. the qx, right? Qx is the can be divided by all these rational all the denominators of the rational function, the rational squares. So qx is the greatest the GCD, the GCD of all these all the denominators. So this is the famous Hilbert 17 problem, which is proved by Artin, such that every non-negative polynomial has a representation as a sum square of rational functions. That means for all the non-negative polynomials, we can find a qx such that qx is a sum square, and the qx times px is a sum square, right? So again, and then this can be solved by SCP. But of course, we don't know the degree of the qx. So the degree of qx could be very large. So in practical, we will we actually first we fix the size of the degree. We give a degree bound of the monomial in qx, and then we set up this this sum square problem, and then we increase the size, the degree bound, so we have a qx larger and larger degree, and eventually, if px is non-negative, then for the degree bound large enough, this problem will be feasible. I.e., this problem can be found by an SDP solver. So this is how can we certify a non-negativity of the this is the way to certify the non-negativity of a multivariate polynomial. Okay.
So Faye, just to sort of make a pause here. So essentially, if px is sum of squares, then, sorry, if px is sum of squares, then so this is if and only if, but when we started out, we had one direction that was simpler.
Yeah. So yeah, so we have a, so suppose we have a px is positive, is negative, right?
Yeah.
And then by the Hilbert 17 problem, we know px can be written as a sum of square of rational functions.
Right.
So and then we just multiply px multiplied by the GCD of the denominators of all the rational squares.
Mm-hmm.
Then which is qx, let's say it's qx. So by going this direction, in reverse direction, we can have qx times px is the sum squares. So px is a sum of rational function, but we can find the qx so that we qx multiply px is the sum of square of polynomials instead of rational functions.
Mm-hmm.
Yeah, so we cannot actually directly solve a sum square of a rational function, right? So if px is rational sum square of rational function, then we multiply it by qs to make it a sum square polynomials.
Okay.
So that's the idea.
Okay, now are you later on going to connect this to, sort of giving certificates for the non-existence of real zeros and things like that, or existence of real zeros?
Yeah. I'm going to.
You're going to do that later. Okay.
Yeah, feasibility, so they call it feasibility. Which is.
It's okay. No, go ahead. I just asked the question. You can continue in your own pace. Yeah.
So this is the. I just want to. This is certify a way to certify the non-negativity of a multivariate polynomial. So multivariate polynomial, we just solve a sequence of SD sum squares or SDP relaxations, and then if the size of SDP is large enough, then eventually we will find this sum squares. So this is the, so we to summarize, we talk about this certificate of a univariate polynomial, which is easy, which is just a simple sum square problem, and the certificate of non-negativity of a multivariate polynomial. This is a little bit tricky, but still, instead of one SDP, you solve a sequence of SDP or sum square problem. So this is a this is certification of non-negativity. Now I want to talk about the non-negativity on set and constraint optimization. Right? Before this is a unconstrained optimization. Now let's talk about the non-negativity, the constraint optimization, so there are two parts. First part, there's sufficient condition and necessary condition. And the sufficient condition, it means so we want to find a sufficient condition for the non-negativity of px over set. Right? So we consider this set is a. Let's first consider this set is defined by these equalities. So then the problem is to decide if px is non-negative on this set S. So a certificate condition for this is true, or px is negative on S is the following. Right? So px we use some multipliers. So px plus some of I equals 1 to m lambda gx fi is some squares. this is easy to see. We are just if this is some square, and then on this S, then all these Fi vanished. So Px will be in a negative. So this is again, this is a sufficient condition. And then we can, how do we actually solve this problem, right? To solve this, of course, we have to fix the degree of lambda Ix. So by fixing the degree of lambda x, so we have some square problem. So i.e. SDP problem. So so the unknowns are the coefficient of lambda x, and then we write this as a matrix product form, and then solve this SDP feasibility problem with unknowns from lambda x. So in a more algebraic setting, this condition, this sufficient condition, can be written as a some square over quotient ring. So Px is a some square. Quotient of this ideal Fix. So the ideal is this Fix is ideal generated by all these constraint Fix. So yeah. So now let's see how can we use this. So this quotient of operation can be done using the Grobner basis of the ideal I. Right. So let's see an example. So we wanna and see how do we convert this to SDP, and how do we quotient this ideal using Grobner basis. So so let's say we want to decide if P is 10 minus x squared minus y is the negative over f. This f is x squared plus y squared minus 1 is 0. So instead we want to we write this polynomial at 10 minus x squared plus y as a matrix product form, and then we expand it. Now we can we model it. We modular we do the modular operations. And this step, in this step, this can be done by Grobner basis. So basically, you replace so y squared is replaced by 1 minus x squared, right? Because x squared plus y squared is 1, so y squared is replaced by 1 squared, and that's the only operation we need to do. Now after this modular operation, so we have less monomials, and then we replace the coefficient of monomials. So Q11 plus Q33 is 10, right? This is the and this is the constant term, and Q12 is 0. Q12 is 0 is the coefficient of x. Here is no x, so this is 0. So Q13 is y, and there's a y, negative y here. So 2Q13 is negative 1, etc. So So and then we solve this sum square problem. So this we want this matrix to be positive semi-definite. And then we get this we have this expression for our polynomial. So 10 minus x squared plus y is equal to this sum squares over the ideal I. So this certifies that 10 minus x squared minus y is in effect indeed non-negative over the constraint. So that's so this quotient over this quotient operation over a ring is definitely more powerful than simply fixing the degree, right? So if we fix degree, then we have to we only have a small subset of candidates. So yeah, so this is how we do it over ring without instead of fixing the fixing the bond, fixing yeah, instead of giving a degree bound of the monomials. Yeah. So this is the now I want to talk about the sufficient condition for inequalities. So instead of equalities, we now have a bunch of inequalities, which is in this form. So we have a bunch of G1x is negative, G1, G2, Gm negative, and of course a sufficient condition for Px negative on S is such that Px can be written in this this following form. Px is equal to x0x plus sum of xix, gix, where s0x and xix, they are all sum square polynomials. So you can see if this is sum squares, then Px is certainly negative, right? Yeah, because x0x is negative, ix is negative, and gix is negative because it's from the constraint. And of course, this can be done similarly using the sum square program or SDP program. This is an example which I won't go through. So in fact, we can have more powerful expressions. In fact, instead of using this form, we can have a more powerful form, which is we actually have a product of the constraint. Right? We want a Px in this form. So where Px is equal to s0x plus sum of xix. So and here is this is gix. Here we have gix times ggx, and basically we can have a 2 to the power of m many terms, because so which is the subset, the number of subsets of the m inequalities. Yeah. So so yes. So the so far I talked about this sufficient condition, right, to certify non-negativity over a constraint, over some constraints. Now let's talk about the necessary condition, right? So necessary, what's the necessary condition? It means it's actually so if it says if px is the negative, then what condition do we have, right? So therefore, if there's a if it doesn't satisfy this if it doesn't satisfy this the necessary condition, then we can show that this polynomial is not a negative. And this necessary condition is usually it's usually infeasibility problem. So yeah, so therefore we want to actually use the necessary condition to show that this is not a negative. We have to certify. We have to do this called an infeasibility certificate. Yeah, because the necessary condition for p being for polynomial being negative is a feasibility problem. So to disprove this the claim, we have to do this infeasibility certificate. And that's why I call the necessary condition as that's why this necessary condition is called the infeasibility certificates. Yeah, so let's say we have this first for linear equality. We consider the linear system xb x equal b, then xb is infeasible if only if there exists u such that A transpose u is 0 and B transpose u is -1. Okay, and this well like the so the one direction is easy, right? If A transpose u is 0, B transpose u is -1, then we have u transpose A u is B u transpose B, and yeah, just from here I multiply this by u by u transpose, multiply it by u transpose, and this becomes 0. This become a -1. So 0 is not a -1. Yeah. So therefore, you can see if this condition holds, then certainly xb is infeasible. Okay. This is the linear equalities, and for polynomials over C, we have this theorem called the Hilbert non-Standard sets. Let Fi Fiz the Fmg be polynomials in complex variables z1, z2, zn. Then Fi is 0, being 0, this is infeasible in Cn, if and only if -1 is belongs to the ideal generated by f1 dot fm. So and then for linear inequalities, we have this Fox lemma, which says if ax plus b equals 0, ax plus b is non-negative. If this is infeasible, then this means if and only if we can there exists lambda non-negative and u is arbitrary, such that this condition this condition holds. So one direction is easy, right? So from this direction to this direction, from this direction, from this claim to this claim, it's easy. Which is this is eventually the weak property of the linear programming, and from the infeasibility to this this condition. This is the difficult condition. It's eventually equivalent to the strong duality of linear programming. Okay, so these are the classic results for infeasibility certificates. So we have, to summarize, we have nice infeasibility certificates for linear equalities, and for linear inequalities, and for polynomials over complex. Well, now we have this. Now we wanna generalize this to reals, right? So these classical results actually can be generalized to handle the case of system polynomials, equations and the e-equations over the real numbers, which is called a theorem called positive Stirling size, which says if fi this fi is 0, so we have a bunch of equalities, m equalities, and a bunch of inequalities g I x negative. This is infeasible in Rn in real, if and only if following is true. That there exists the fx and gx in Rx. Rx is the multivariate polynomial ring, such that fx plus gx is -1, and fx is in the ideal of f1 generated by f1 the fm, and gx is in the pre-order of g1 the gp. So what is the pre-order? Pre-order, the definition of pre-order of a bunch of polynomial is the following. So see the pre-order of g1, g2, gm consists of all the polynomial g, such that g is S0 plus the sum of the first term is Si times Gi, and then they have two indices, Sij plus times Gi times Gg, and Sij Igk times 3, the product of 3 Gi, Gg, and Gk, and etc. So and where is this coefficient S0, Si, Sij, Sijk. These are all these are all sum squares. Okay, so the S alpha, this coefficient S and this S are all sum squares. So the sum is finite. So there with 2 to the power of m terms. Because we can say this IJK, they are they're just a subset of GI G2GM, and there are two to the power m subsets. So the sum is has the 2 to the power m terms. So this is the preorder. This is the definition of the preorder. So this infeasibility, if you want to certify this infeasibility, the infeasibility of this this polynomial constraint, and then this is equivalent to actually a sum square problem, right? Yeah. So let's say an example. Let's say example F1, G1, G2. So F1 is x squared plus x2 squared minus 1, 0. G1 is 3 times x2 minus x1 to the power 3 minus 2 being a negative. G2 is x1 minus 8 x2 to the power 3 being a negative. Now, now that by the so we want to certify if this is infeasible. So by positive Stalin says this system is infeasible if and only if there exists a polynomial T1, S0, S1, S2, S1, 2 in this in R X1, S2 such that this condition holds, right? So here we have this condition holds. This condition fx plus gx, and this is the preorder of G1, G2, which is gx, and here is F1, T1 is the ideal. The ideal of F1 is comes from the ideal of F1. So here we have this is fx, right? And yeah, and there are only how many terms, right? 1, 2, 3, 4, because we only have two equations, two inequality. So 2 to 2 is 4. So four terms from this this summation. Yeah. So now how do we actually how do we actually use this condition? How do we actually to show that there exists such a polynomial, there exists this polynomial such that this condition holds? So first we need to bound the degree of all the monomials by D. So the degree bound is given by capital D. So all these monomials, F1 times T1, the degree is less or equal to D, degree S0, degree S1, G1, all these 1, 2, 3, 4, these 5 terms, the degree of the monomials in this on the left hand side is bounded by the capital D. Now we given a degree bound, we can for each degree bound D, there's a corresponding sum square STD problem, right? Because this S0, S1, S2, X1, 2, they are all sum squares. This is the and then the unknowns are and the number of unknowns, which is actually just the coefficient of this f1, s0, s1, s2, s1, 2. And these are the number of the unknowns are bounded by this degree, by degree d. So this is the corresponding STP problem, or some square problem. So for instance, when we let degree bound d is equal to 4, then we solve this corresponding sum square and STP. We did find this is feasible. So we get this T1 S0 and S1 S2 F0. So therefore, we have certified that by solving this STP problem, and given this degree bound d, we have shown that this polynomial system is in fact infeasible. But of course, now that if d is equal to 4 doesn't work, you may want to consider you increase the degree bound d, right? So yeah, if d doesn't work, then you try 5, and then if 5 doesn't work, you try 6. Each time you have a larger STP problem, and eventually for d large enough, you will find such a certificate. Given that this polynomial system is indeed infeasible, right? This is because of the positive standard size. There must exist somewhere, somewhere for some degree, there must exist this polynomial. So therefore, for d large enough, eventually you will be able to certify its infeasibility. Okay. Yeah. So that's I think that's what you said, Mira, about the infeasibility certification.
Yeah. Correct. Yeah. Yeah, that's good.
So are there any questions so far? Okay. If there are no other questions, then I will proceed. First, yeah. So far I define this pre-order. You can see the pre-order is quite quite large. It's a pre-order of this G1 data is it's very large set. Like the elements in the pre-order have very high degree, right? Because you have so many terms, and each term has it's a product of other polynomials. So the degree is very large. That means our sum square or STP has a very large size. This is not this means in practice this is not good. We don't want to have our problem to be too big. So now we have we define a different we introduce a different definition, which is called quadratic modular, which is much simpler than the pre-order. So this definition of a quadratic modular module G1 .gm it defined is such that all the polynomial G, such that G is equal to S0 plus S1 G1 plus dot dot plus SM GM. So there are no products of the G's. So here, of course, this S0, S1, SM, these are some square polynomials. Now let's study this polynomial optimization over S. So we consider this problem. Yeah. So we want to solve this polynomial optimization over set S by a hierarchy of relaxations. So let's consider this optimization problem. Consider P star is the minimizer of Px. Px is a multivariate polynomial over S. S is a what? S is a constraint. It's a set defined by this polynomial inequalities, right? So this is a very generally a non-convex problem, which means it's hard to solve. Yeah, because this polynomial could be this non-convex. This constraint, this S could be non-convex. So this is a in general a non-convex optimization problem. So how do we actually how do we solve this? How do we actually treat this deal with this problem, right? So the idea is the following. We want to the idea is it's called the hierarchy of relaxation. So for at each step we solve a convex optimization problem, and then each step we have a degree bound, and then we solve a convex optimization problem, and then we increase the degree bound at each step. So by increasing the degree bound, we have a larger, we have a better approximation of the original non-convex problem, and eventually we have a sequence of a monotone. We have a monotone sequence of optimum values, which will converge to the global optimum point of the original non-convex problem. So the idea is the following. So we instead this minimization problem, we consider this this maximized problem. So we instead maximize gamma, so that Px minus gamma is in the pre-order of G1, G2, Gm, right? Pre-order here. This is just this P1 is just so P1. So you said so P1 minus gamma should be non-negative, right? So this is and also or we can solve this problem. P2 it's the we maximize because the maximizer of gamma, so the Px minus gamma is in the Q modular of quadratic modular of G1, G2, Gm. So yeah, this is the two this one. The first one is called the Schmilgen representation. The second one is called the Putiner representation. And now we are given a degree bound D for the sum squared polynomial in pre-order of the quadratic modular. Right, then we give it degree bound. Then this then we can maximize over gamma via through the sum squares, and it's SDP problem. So yeah, and then this year actually prove that that as our degree D degree D increases, then this P2 actually converges to P star. And I think similarly, P1 also converted to P star.
So, Faye,
yeah,
at something like the Dth level or of the Lassé hierarchy or SOS hierarchy, you're supposed to get polynomials of degree 2 times D or something like that. I mean, then you have to lose something. There's no free lunch, right? I mean, if you're convexifying, then whenever you do convex relaxation, somehow the complexity, you're increasing variables, right? You're adding R.
Yeah.
Right. But also somehow the degree should go up.
Yeah. Yeah.
Or something like that.
Yeah. So the degree for the sum squared, right? In the
yeah.
So I convert. So in this pre-order or the quadratic modular, there is this sum squared, right?
Mm-hmm.
Of course, if we don't have the degree bound, then this is equivalent. But then in theory, in practice, we can only solve it for given degree bound.
Mm-hmm.
So yeah, so when we increase, when you have the degree bound larger, then this become there are more monomials, right?
Right.
So yeah, so then we have better approximation, but the computational complexity is much higher.
Uh-huh. Okay, thanks.
Yeah, that you lose something when you increase the degree bound. The degree bound, then you get then the sum squares here involve have larger have more monomials. Yeah. Therefore, so yeah, this is actually called the Lassé hierarchy, right? But the Lassé hierarchy basically proves that you can actually approximate this global you can find this global optimization of a polynomial optimization problem in this form by solving a sequence of this convex problem, such that Px maximize gamma and the Px gamma is in the truncated Q quadratic modular. So the degree is why it's called truncated, because we bound the degree of the sum square terms to I think for pre-order, although he didn't prove the Schmidt representation, but similarly, I think it's true. It's true also. So generally, you can solve it using both both representations, and then eventually it will converge. But it could be arbitrarily close, right? It could be arbitrarily close. There's no guarantee that this will stop at some finite degree d. So you could instead you keep increasing degree bound d, and then you are getting better approximation, but you may never have actually reach the global optimal. So that means, so now so to actually to study then we to study this kind of a problem, right? We want to study this finite convergence of hierarchies. So we want to know when under which condition is you get an exact approximation. So for some degree d, this convex approximation exactly solves the non-convex optimization problem. So I see. First, we need a definition of the Archimedean. The definition is the following: a quadratic module is an Archimedean if there exists R in N the natural number, right? Such that is R minus the sum square. It's the sum of xi square. This is in the quadratic module. So we say this quadratic module is has this Archimedean property if it satisfies this this condition. Note if this the quadratic module is Archimedean, then this S is compact, and because S is contained in the ball that this sum of si square is less or equal to n. So this S is compact. If it's X is compact, then we can prove lots of nice properties. So now we can study this general problem. This polynomial minimization problem. Fi minimize Fi such that Hix is 0. I is there's M1 equalities, and there are J. There are M2 inequalities, right? So minimize Fi Fx, Hix is 0, Gix is the negative. And then we consider this hierarchy of S sum square relaxations. So we want to maximize gamma such that such that this such that F, yeah, sorry, I think there's something missing there. Yeah. Q, yeah, px minus r.
Yeah.
Such that such that fx fx minus r, right? Minus gamma, yeah. Yeah. So maximize gamma such that fx minus gamma is in this h2k plus qkj. So where this h square bracket h square 2k is a 2k is truncated ideal generated by h, right? Yeah. For truncated ideal, I mean all these ideal that's f so suppose h is h1 hm1, and then hk h2k is the all these the h2k consists of all the polynomials like p as p, so that p x is equal to t1 x hi x plus plus t t mx hm, and the degree p is less than or equal to 2k. Yeah, this truncated means all the you just truncate the ideal, right? The ideal you just throughout all this polynomial that has degree larger than 2k. And
so is it sorry, is there another version of this hierarchy where you bound the degree of the TIs?
Yeah, you bound degree of TI. Eventually you bounding the ideal, right?
That's true, but they're slightly different, right?
Yeah. They're slightly different. Yeah, I think this is the version of bounding the degree of the ideal. Yeah, but previously, what I'm talking about, I'm bounding the degree of the sum squares. Yeah.
And it's the same definition for QK?
Yeah, QK is the same thing. It's the case truncated quadratic modular generated by G.
Okay. Okay, thanks.
Actually, yeah. And then we have this theorem by Nie. So that under this condition, Archimedean condition, for this, so that means R minus some square I square is in this truncated ideal H2t plus QTJ for some t in the natural numbers, but being integers, and R is positive. And then if the constraint qualification, a strict complementarity and second order sufficiency condition holds, and then at every global minimizer of the blue one, right, the original non-convex problem, then the hierarchy has finite convergence. So it means for some finite k, this non-convex some square problem exactly solves the non-convex optimization problem.
So are there any bounds on the number of levels?
Yeah, there is I think for some particular problems.
Okay,
like for the,
but it's
for
not
some,
a general condition on the original whatever. Yeah. I guess I can't see properly here, but
this original.
The original problem. Okay, yeah.
Yeah, but for some like 0, like 0, 1, like integer programming problem, there is actually a degree bound.
Okay.
Because let's see, I can write a if I have a x being 0, 1, then this can be replaced as a square minus x equals 0.
That's right. Yeah.
And so suppose I have an integer programming problem. I maximize some fx such that x is 0 to 1. Then I replace this one by polynomials. Then I use this as some square hierarchy. There is actually a degree bound for that. I think the series has a paper. Has paper. Let me just write on my. So yeah, Lucia has a paper, I think, for the bound of the sum squares for the integer programming problem.
Okay.
Yeah, but it is exponential.
It's exponential, but it has this property for it has finite convergence. That means some finite number of levels will actually be sufficient, and then you're saying that number of levels is exponential.
Yeah.
In the number of variables of the original problem. I mean, for integer programming, you can always assume it's quadratic, right?
Yeah. For the number of the variables.
Yeah, number of variables. Okay.
Yeah, actually, Parallel has a, I think Lawrence, Monica Lawrence has a paper. Improve this bound, and then Pablo also has a paper using some group theory to improve this bound. This paper, exact. Yes, yeah. Maybe what's the name of the paper? But anyway, I can find the paper later.
Yeah, maybe you can put it in the chat or something, or send it by email, and I'll send it to the class.
Yeah.
Okay. I mean, that's a very important case of 0-1 programming.
Yeah.
Yeah. So, okay, just continue, please.
Yeah. So yeah, I want to explain this. This and this condition, right? This constraint qualification. What's this constraint? So constraint qualification, it means what? It means basically there's a subdifferential of gx is linear independent and linear independent, and a strict complementarity means what means lambda I lambda I gx whatever yeah lambda I lambda as optimal solution lambda lambda star gx star is 0, and 3 second order observation condition, it means the Hessian yeah, it's the Hessian matrix is a positive definite, something like that. But basically it says this property holds generically. So this property holds generically. That means for most of the problem you see in practice, you will have this finite convergence property. Yeah. So yeah, if you all know this, there's a paper, right? There's a paper by Zhang Wang. It's called optimal condition and finite convergence of a Rassier hierarchy. Optim. Of a Rassier hierarchy. So yeah, I guess this is what I want to talk today.